Okay, another video from 1.7 talking about inverse functions. In this video, I'm going to deal with an example, the example of a linear function. In fact, the specific linear function that I want to look at is one that I already talked about in a previous video. In this first video where I was doing an introduction, I started out with the function f of x equals 3x minus 2. And I claimed that the inverse for that function was x plus 2 divided by 3. This is the function that I want to look at in this video. I'm going to show how we could come up with this as the inverse function. We'll look a little bit into the graphs of these two functions, and we'll look at what happens when we compose the two of them together. So we have this function f of x equals 3x minus 2. And the first thing I want to do, which is probably the most important learning objective, is finding the inverse of this function. And what you'll see is it's not too bad for this function because this function is relatively simple. It's a linear function. We'll kind of learn the process with an easier example, and then in a future video, I'll make a harder example, and we can kind of practice out these steps on a harder example. So suppose you're given a function, you want to find the inverse. What I like to do is think about this as a three-step process. And I actually just changed my mind. I'm going to call this a four-step process, although some of the steps you'll see are kind of trivial. The first step, if you're trying to figure out the inverse function, what I'm going to say is always just change your function f of x or g of x or whatever it is, change the f of x into a y. So I'll put f of x in quotation marks because it might be a g of x or an h of x. What I'm saying is just rewrite the function that you're given, except instead of an f of x, write the letter y. That seems like a stupid step. Why are you doing that? Well, it's going to turn out that I'm going to do a lot of algebra here, and it's easier to do algebra with the y floating around than an f of x floating around. Maybe that's just personal preference. I think it'll make your life easier to do this first step, even though you could argue that that's not really necessary. Even though it doesn't seem like we've done much, I think about this as a function, whereas I think about this as an equation. So this was the original function we were given. This is an equation that represents that function. And I know it seems like I'm nitpicking on semantics, but I think differentiating the two of these guys will help you remember what we're doing here. So I now have an equation that represents the original function. My second step is to switch my variables, change my x's into y's and my y's into x's. So doing that is as easy as it sounds. Where I see the letter y here, I'm going to write the letter x, and where I see the letter x here, I'm going to write the letter y. And it's possible that my function has multiple x's in it. That's fine. Just change all of the different x's into y's. All I'm doing is everywhere I see an x, I write a y. Everywhere I see a y, I write an x. Doing it's easy. Why am I doing it? Well, the argument here is this is an equation that represents the function. But remember, my goal is to find the inverse function. So what I want is an equation that represents the inverse function. And because all an inverse function does is it switches the inputs and the outputs, and the letter x is what we're using for the input, and the letter y is what we're using for the output. If we switch the x's and the y's, the inputs and the outputs, we'll change from an equation that represents the function to an equation that represents the inverse function, which is what we have right here. It doesn't seem like we've done much so far, but we're actually really close to the final answer. Most of the work is still yet to be done. But this right here is an equation that represents the inverse function, so it's really close to what we're looking for at the end. The only problem with this equation is it's not written in function notation. Function notation has to represent the output in terms of the input. Our third step will just be to solve this equation for y. And you look at this and you're like, that's not too bad. Get this y by itself. I guess you'd add 2 to both sides of the equation. So you'd get x plus 2 equals 3y, and then you divide both sides of the equation by 3. So you'd get x plus 2 divided by 3 equals y. And yeah, in this case, it wasn't that hard to solve for y, but really that's just because we started out with a pretty basic function to begin with. Imagine this was some other function, and maybe there were multiple x's floating around. Well, then when I switch all the x's into y's, I'm going to have multiple y's floating around. And solving an equation when you have multiple y's is a lot more challenging than solving this linear equation that we have here. But don't worry too much about that. The purpose of this video is not to solve those more challenging functions. It's just to understand the steps that we'll be doing when we solve those more challenging functions. We're basically done here, and when I originally said this was just a 3-step process, I was planning on just calling this good. But I should be a little bit careful. We shouldn't call this good because this is not an inverse function. This is an equation that represents the inverse function. To write this as an inverse function, I have to use function notation. Instead of writing y, I want to write f inverse of x. My fourth step is kind of like my first step. I just have to change my y's back into their functional equivalent, which in this case will be f inverse of x. Note that I'm putting f inverse of x in quotation marks again, because if your original function were g of x, then you'd want to write g inverse of x, for example. It's not super important, but just like the f of x on the left-hand side kind of looks prettier, my f inverse of x over on the left looks a little bit prettier as well. So I'll switch which side of the equal sign this stuff is on and write my final answer like this. The good news is that this same 4-step process will work for finding the inverse function of any function that you're given, not just linear functions. The bad news is that I'm kind of hiding the fact that step 3 can be really challenging. when you solve for x here, there could be a lot of work. In this case, there wasn't that much work, but generally speaking, like 90% of your work comes in this third step. Steps 1, 2, and 4 are all kind of trivial, but I want to write this as a 4-step process because for a lot of people, they'll look at one of these and not know how to get started. It's worth pointing out that this x plus 2 over 3 is exactly what I claimed the inverse function was up here, which is good. That means I don't have to go back and redo another video. But if we weren't sure, if we were worried that we made a mistake, we could use the fact that a composition of a function and its inverse is always equal to the identity function to kind of check our work. I'm going to add a step 2 here, which you certainly should not always do. You don't need to always check your work. If you did these steps correctly, you got the right answer. But I just want to demonstrate how you could check your work. And I'm going to do it twice. I'm going to compose together these two functions, the function and its inverse, and I'm going to do so in both orders, f of f inverse and f inverse of f. So first, f of f inverse of x, I think it's easier to rewrite this in this notation because then all you have to do is replace f inverse of x with what you just said f inverse of x is equal to. So inside these parentheses here, instead of writing f inverse of x, I'm going to write x plus 2 over 3. And so what I have is f of x plus 2 over 3, and I can figure that out because I have f of x written up here, and this is like a blueprint telling me the output for this function for x as the input. What I want is the output for this function as if x plus 2 over 3 is the input. So I copy exactly what I see written right here, except I change all of the x's that I see into x plus 2 over 3. So I have this 3 times, and then instead of writing the letter x, I'm going to write what's inside these parentheses, x plus 2 over 3, and then I have minus this 2 from up here. And if I simplify this thing a little bit, this 3 and this 3 cancel out, so I have x plus 2 minus 2, and plus 2 and minus 2 cancel out, so I just get x. Oh, that's kind of weird. Nah, it's not weird at all. When you compose together a function and its inverse, you should just get x. What this is saying is if you take something and you put it into the inverse function and then into the function, what's going to come out is exactly what you put in. Oh, that makes sense because the inverse function and the function kind of undo what each other do. So whatever changes the inverse function made, the function undoes, which is what this is telling me. This is sufficient for me to believe that I didn't make any mistakes in my algebra earlier. If I really were going to check this, which again, I typically don't do, I'd be happy at this point. But just for the sake of demonstration, I want to point out that you could also compose those functions together in the other order. I could figure out f inverse of f of x by doing the same thing that I did before. Start working from the inside out. So instead of replacing f inverse of x with what it's equal to, what I'm going to do is replace f of x with what it's equal to. Up here I wrote f of x equals 3x minus 2, so I'm going to replace this f of x with 3x minus 2. And then I'm going to say I'm trying to figure out what f inverse of this is. Well, here's a blueprint that tells me the output for this f inverse function when x is the input. So I'm going to copy this output, except I'm going to change all the x's into what I see inside these parentheses. I'm going to write 3x minus 2 in place of this x right here, and there's some unnecessary parentheses, plus 2 divided by 3. Let's see if I can simplify this. These parentheses aren't doing anything. I only wrote them there to help you see that this x is being changed into this 3x minus 2. But because they're not being multiplied by anything, I don't even need these parentheses. Really, what's written in this line is equal to what's written in this line, and now it's easier to see how the simplification is going to happen. This negative 2 and this positive 2 cancel each other out, so I'm left with 3x over 3, and then this 3 and this 3 cancel out, and I'm left with just an x. Oh yeah, that's exactly what I was expecting to get. If I compose together the function and its inverse, I'm left with just the identity function. The third and final thing that I want to do in this video is I want to sketch a graph of the function and its inverse function, because it turns out that the graph of these two things are related in some sense, and I want to make that sense clear in this video. So graphing is one of those things that people have different levels of comfort with. I'm going to assume that you're able to graph linear functions. So when you see f of x equals 3x minus 2, maybe you're thinking y equals mx plus b. The b in this case is the negative 2. This refers to my y-intercept. This is telling me that my graph is going to go through this point right here, negative 2 on my y-axis. And then this 3 right here refers to the slope. It helps to think about the slope as a fraction. So instead of just writing 3, I'm going to write 3 divided by 1. Rise over run is something that a lot of people say to help them remember this. This 3 is the change in the y-coordinate for every 1 change in the x-coordinate. So what this means is from this point, I want to go up 3 units, 1, 2, 3, and then to the right, 1 unit. This tells me how far I go up. This tells me how far I go to the right. Now that I have 2 points, and since I recognize this was a linear function, I know I can connect them with a straight line. So I connect those points with as best of a straight line as I can make on my computer, and I get that this is the graph of f of x equals 3x minus 2. And you're a little bit bored. You're like, what are you doing here? Why are you wasting my time? Well, really the idea is I want to graph both f of x and f inverse of x and show you how the graphs are related. And I'm going to show you two different ways to graph f inverse of x. The first way is I can just graph this function. And if you know how to just graph this function, great. What you do is have to recognize that it's a linear function. It's a little bit hard to see when it's written in this form, but when you have a sum divided by a single number, you can rewrite that as a sum of two fractions. What I'm saying is we can call this x over 3 plus 2 over 3, and we could rewrite that x over 3 as 1/3 x plus 2/3. And these are two steps that I kind of take for granted, but they're really important. They're really good algebraic steps for you to be really comfortable with. The step from here to here, note that you can only do that if you have a sum in the numerator, not in the denominator. If this were x divided by, I don't know, y plus 3 or something, you could not break this up into two different fractions. You can only break up sums in the numerator divided by the denominator. If you have a hard time remembering that, think about fractions. Think about if I asked you, like, what's 2/7 plus 1/7? Well, what you would say is that's 3/7, right? Where you're getting that 3/7 from is the 2 and the 1 up in the numerator you're adding together. When you have fractions that have the same denominator, you leave the denominator alone and you add up their numerators. So going from this line to this line typically makes sense for students, but if I can go from this line to this line, then it makes sense that I can go from this line to this line. The other step that's really important is you want to be able to rewrite things like x over 3 as 1/3 times x. And again, it's easier to go up than it is to go down. If you had a fraction times a number, 1/3 times x, what you can do is you can think about that x as x divided by 1. The logic here is I don't know how to multiply together a fraction and a whole number, but I can certainly multiply together two fractions, and I can change this whole number into a fraction. So the way I think about this is 1/3 times x. I'm thinking 1/3 times x over 1, and then when you multiply fractions, you multiply straight across. So this 1 times this x gives me an x, and this 3 times this 1 gives me a 3. What I'm saying is 1/3 times x is the same as x over 3, and therefore x over 3 is the same as 1/3 times x. In both cases, it's easier to see that this equals this and that this equals this than it is to go down in this direction. But the argument is equality works both ways. So if you see how this is the same as this, then you're seeing how this is the same as this. And being able to go from this to this to this, those kind of algebraic steps will be really useful both in this class and beyond. At any rate, the advantage to rewriting this inverse function in this form is now it's y equals mx plus b. I could find the y-intercept, and I could find the slope, and I could use that to create the graph that I'm looking for. But that doesn't seem like a whole lot of fun, right? A y-intercept of 2/3, but that's somewhere in here, I guess, and then a slope of 1/3. So I have to go up 1 from this already fractional spot, 2/3. So I guess that puts me up here somewhere, and then over 3. I guess that puts me somewhere over here, and I got to try my best to connect those with the straight line. I'm not really excited about that. But what I could do is I could think about the graph a different way. I could think about the graph that I'm about to sketch in green of the inverse function just in terms of the graph that's listed here in red. Because the graph that's listed here in red, I already have a couple nice points on here. And when I say nice, I mean integer coordinates. This point right here has an x coordinate of 0 and a y coordinate of -2. And this point right here has an x coordinate of 1 and a y coordinate of 1. What it means for this point 0, -2 to be on this graph is when the x coordinate equals 0, the y coordinate equals -2. What I have here is an input-output pair. It's saying when I put 0 into my function, -2 comes out. Wait, if I put 0 into my function and -2 comes out, I know that when I put -2 into my inverse function, 0 must come out because all the inverse function does is it switches inputs and outputs. So if 0, -2 is on the graph of my function, then it must be the case that -2, 0 is on the graph of my inverse function. -2, 0 is over here. So because this point is on the red graph, this point has to be on the green graph. Similarly, because this point at 1, 1 is on my function, it's on the red graph. If I switch the x's and the y's, well, they're both 1s in this case, you can't really even see anything. This 1 will become the input to my inverse function, and this 1 will become the output for my inverse function. So what that means is my green graph must go through this point as well. And now I have these 2 points. I don't have to worry about rewriting this algebraically, thinking about slope and y-intercept. I can just connect these 2 points to come up with the graph of my inverse function, f inverse of x, which I can either write in this format or this format, it doesn't matter. And I'm done graphing. Some general points that I want to make. There's some nice symmetry going on here, right? If you had to describe the red and the green, you'd say there's some sort of connection there. I mean, I don't know quite how to describe it, but there's sort of some pattern going on. Well, really what's going on is when you switch the x and y coordinates in a graph, what you end up doing is reflecting over the line y equals x. The line y equals x is this diagonal line because, again, you can think y equals mx plus b. The b is a 0 and the m is just a 1, so I go up 1 and over 1. This diagonal line right here is the line of symmetry in between your function and your inverse function. And that's not specific to linear functions. That'll always be the case. And it makes sense that that's the case because all I'm doing for the inverse function is I'm switching inputs and outputs. The 0, -2 that represents this point that I had mislabeled a second ago, sorry about that. When I switch the input and the output, I get this point at -2, 0. Switching the input and the output of all of the points on a graph is equivalent to just reflecting over this line y equals x. That's a lot for one video, but it really captures all the key ideas for this section. When you have a function, you want to be able to find its inverse function algebraically. It's good to be able to check that functions are inverses of each other by doing function composition. And then we also want to look at this more geometrically, looking at the graphs of a function and its inverse function, and recognize that there's always going to be this nice symmetry because the inverse function just comes from switching inputs and outputs. And switching inputs and outputs on a graph creates this nice symmetry reflection over the line y equals x.